Good morning, everyone. My name is Fei Long, today's presenter for this paper. Unfortunately, the first author of this work, Zhongxu Guan, is unable to be here today to present this research in person. I will present this work on behalf of the entire author team. The name of this work is BayWatch, Practical Internet Scale Topology Monitoring with Dynamic Bayesian Estimation. This is a collaborative effort with Zhongguancun Laboratory and China Telecom. Internet topology monitoring is important because it serves as the foundation for outage detection, fault diagnosis, and understanding global connectivity. In practice, commercial systems have already demonstrated the value of topology monitoring. However, most of them are designed for enterprise or data center environments. At the internet-wide level, only a few systems monitor connectivity dynamics, while academic research still focuses more on topology measurement than on continuous topology monitoring. Now, let's move from why topology monitoring matters to why it is technically hard. The key challenge is that the internet paths are often multipath. A path from one source to one destination is usually not a single deterministic path. Because of equal cost multipath routing and load balancing, the same source-destination pair may traverse multiple next hops. As a result, the path may branch at one router and reconverge later, forming a diamond-like multipath structure. This is important because a single observed trace does not reveal the full structure behind the load balancer. Traditional tools such as traceroute and even faster probing tools like YARP usually reveal only one realized path at a time. So if our goal is complete topology monitoring, we must discover the whole multipath structure, not just one observed trace. This naturally leads to the next question: how can we systematically uncover these hidden branches? The answer is multipath detection algorithm. Traditional MDA addresses this problem by sending multiple probes to the same destination, but with randomized flow identifiers. Once the probes reach a load balancing router, different probes may be forwarded along different branches, so MDA can gradually uncover multipath successors instead of just one realized path. It works hop by hop and round by round, and it keeps probing until missing another branch becomes statistically unlikely. So the main idea of MDA is very elegant. It discovers multipath by randomizing flows and using a statistical stopping rule. The key question now is how MDA decides when it has seen all branches. Its answer is statistical. MDA estimates the probability that one branch is still missing after sending several probes. It keeps sending randomized probes to the same destination and asks, after these probes, what is the probability that one branch is still hidden? The crucial assumption is that the load balancer splits traffic uniformly. In other words, every successor is assumed to be equally likely. Once we make that assumption, the miss probability becomes easy to compute. If one branch remains unseen after n probes, the probability of still missing it decreases exponentially with n. For example, if there are two equal likely successors, then after n probes, the missing probability is 1/2 to the power n. After 6 probes, this is about 1.6%, which is already below 5%. So MDA can stop and claim a 95% confidence guarantee. This is why the uniformity assumption is so important. It is exactly what makes the statistical guarantee possible. But the original traceroute-based MDA is still too slow for internet-scale measurement. That is why dminer later combines MDA with YARP so that the same idea can actually scale to the internet. These slides explain what dminer adds on top of classical DMA. MDA already gives a statistical guarantee, but is too slow to run at the internet scale. YARP makes probing fast, but because it is stateless, randomized, and parallel. dminer combines the two. It keeps the MDA logic, but uses YARP to make internet scale probing practical. But the important point is that the dminer only fixes scalability. It still relies on the same uniform splitting assumption as MDA. So YARP makes MDA scalable, but not assumption-free. What really matters here is not the true hidden distribution inside the network, because the observer at S never gets to see that directly. What actually observes is shown when the star aggregates the non-responsive or indistinguishable branches. So if we want to compute a statistical guarantee, it should be based on this observed distribution, not on the inaccessible true distribution. And that is exactly what a naive uniformity assumption can fail in practice. So we ask a simple question: does the real internet actually look like that? We measure the response distributions of load balancing routers in the wild internet and use the Gini coefficient to quantify how uneven they are. What we see here is that only about 1/5 of diverged nodes are close to uniform, while many others are clear uneven. So in the real internet, uniform load balancing is the exception rather than the rule. And once that assumption breaks, the classical statistical guarantee becomes unreliable. So the next question is not just whether the uniformity assumption can fail, but how much damage that failure actually causes. To answer that, we evaluate D minor on controlled topologies. As the Gini coefficient increases, D minor recall drops rapidly. At GC is 0.4, D minor misses 24% of nodes and 60% of links. So once the uniformity assumption breaks, MDA style method can miss a substantial fraction of the topology in practice. Besides the completeness of topology, the efficiency of monitoring is also a crucial problem. A straightforward approach is to repeatedly collect independent topology snapshots, but most paths remain stable over time, so repeated probing mainly revalidates already known edges. Continuous monitoring should reuse history rather than rediscover the internet from scratch. To model forwarding probabilistically, we need a structural assumption that is both simple and reasonable. Our intuition is that IP forwarding is hop by hop. At each hop, a router makes its forwarding decision based on its local state and the packet header, rather than on the entire path history. So from a modeling perspective, the next hop should depend mainly on the current hop. This naturally leads to a first-order Markov model. Now let me explain how BayWatch turns topology into a Bayesian network. The key idea is to organize all nodes observed at the same TTL into one layer. So instead of thinking about the topology as one irregular graph, we represent it as a layer structure. Then edges are placed only between adjacent layers. Each edge carries a forwarding probability which describe how likely a probe is forwarded from one node at the current hop to a node at the next hop. In this view, the load balancing response distribution is exactly the transition probability between adjacent layers. What we directly observe at the probe replies, but the actual forwarding choices inside the path are hidden. So once we write the problem in this way, topology discovery is no longer just a probing problem. It becomes a parameter estimation problem. We estimate the hidden transition probabilities that best explain the observation. These slides explain what parameter estimation means in BayWatch. On the left is the hidden forwarding structure between adjacent layers. In the middle is that what we actually get from measurement, a sequence of probe replies. So we do not directly observe the true forwarding probabilities. What we observe is only a partial footprint of them. This is why BayWatch needs hidden inferences. It used the observation to infer the transition probabilities between adjacent layers, which correspond to the partial LBR distribution. The key question here is not how many probes are needed for one branch, but how many probes are needed for the whole hop. This hop level budget depends on two factors: how many probes are needed to cover the successors of a node, and how likely a probe is to actually reach that node. So if a node is hard to reach or its rare successors are easy to miss, the required probe budget for that hop becomes larger. Let me first show how BayWatch works in bootstrap mode, where no historical snapshots are available. In this case, BayWatch cannot rely on prior measurements, so it starts with an initial round of randomized probing. Following the standard practice, this first round is used to obtain a coarse initial topology. Then BayWatch organizes the discovered nodes by TTL, which gives us a layered Bayesian network representation. But at this point, the topology is still incomplete. Some branches may simply not have been observed yet. So BayWatch explicitly adds hypothetical unseen nodes, showing here as the start nodes. These hypothetical nodes represent the possibility that another successor may still exist, but has not been yet discovered. This initialized Bayesian network is then used at the starting point for the next round of estimation and probing. After the first probing round, BayWatch updates the Bayesian network using the new observations. Some hypothetical nodes are confirmed and become real discovered nodes, while unsupported ones are removed. The key point is that BayWatch does not restart from scratch. It updates the current network and computes additional probes only for the uncertain that still remains. So the topology becomes more accurate and the probing becomes more focused. Until BayWatch confirms all visible paths are seen, it stops. If we evaluate BayWatch in two complementary settings, first, we use 100 representative controlled topologies and vary their average Gini coefficient from 0 to 1. This gives us ground truth with different levels of load balancing skew, so we can evaluate both estimation accuracy and topology completeness. Second, we evaluate BayWatch at the internet scale by probing all route table IPv4 prefixes, which gives us 14.46 million targets. The first question is whether BayWatch can accurately estimate the practical LBR distribution. We compare the estimated LBR distribution with the ground truth using Jensen-Shannon divergence. When GC is less than 0.5, the average JSD stays close to 0. This covers 89.4% of divergence nodes in the real internet. So for the vast majority of practical cases, BayWatch can estimate the LBR distribution very accurately. The next question is the completeness of BayWatch. We compare node and link recall on controlled topologies with different levels of load balancing skew. As the Gini coefficient increases, D-minus recall drops quickly, especially for links. BayWatch remains much more robust because it estimates the practical LBR distribution instead of assuming uniform splitting. Accurate distribution estimation translates it into better topology recall. And the next question is the completeness of, in the internet scale, we deployed BayWatch. Compared to the state-of-the-art method of MDA, Bermuda discovers 2.5 times nodes and 3 times links of D-minor in the 3 snapshots. The improvement is not only in the aggregate topology. For many individual prefixes, BayWatch discovers far more nodes and links than D-minor. This shows that BayWatch reveals much richer multipath structures rather than just adding a small number of extra edges globally. These two plots explain why BayWatch discovered a much larger topology. The top plot shows that the BayWatch keeps discovering new nodes and links across rounds while D-minor saturates quickly. The bottom plot shows that the D-minor resolves prefixes too early, whereas BayWatch keeps probing longer. So the difference is not only how much topology is discovered, but also when the algorithm decides to stop. Okay, let me summarize the predictive mode. BayWatch uses historical snapshots to predict the next LBR distribution with a DBN, then verifies that the prediction with probes and falls back to the bootstrap mode when needed. This slide asks a simple question. Does the historical model really help prediction? We compare the predicted LBR distribution against the ground truth using KL divergence. About half of the predictions are exact matches, and nearly 80% have KL divergence below than 1. So compared with a uniform distribution baseline, BayWatch improves prediction accuracy by about 20%. A natural concern is whether predictive mode might miss too much topology. This table shows that the answer is no. Across these snapshots, the final node and link counts are almost identical, so prediction helps us start from a much better prior, but it does not significantly change the final topology we recover. The completeness loss is below 1%. So let me end with 3 takeaways. First, uniform load balancing is not a reliable assumption in the real internet, so classical MDA-style methods are often incomplete. Second, BayWatch uses Bayesian estimation and temporal prediction to recover the practical forwarding distribution. Third, this gives us both the more complete topology and more efficient monitoring, and it even enables anomaly detection. So the main message of this work is that BayWatch turns internet topology discovery into practical continuous monitoring. And this is the end of the presentation. In this work, we present BayWatch, which improves multipath topology discovery under non-uniform load balancing and further reduces the overhead of continuous monitoring through prediction-driven probing. The code, website, and contact information are listed on the slides for reference. Any questions on BayWatch, please mail to the following address. Thank you very much for your attention.